Welcome to a new episode of BFRR, our Bitcoin, Fiat, and Rock'n'Roll podcast that explores the intersection of traditional finance, digital assets, and digital currencies, and ultimately also helps you understand how digital money and assets will evolve in the future. I'm Jonas Groß, and in today's episode, we are talking about privacy-enhancing technologies. So, why is this a topic that is of importance? So due to technological innovations, tools have emerged that can help us strengthen, regain our privacy in an increasingly digital world. So basically a world where privacy is more important than ever from my perspective. And one such tool are so-called zero-knowledge proofs, or ZCPs, basically an innovation that has made massive progress over the past years with tremendous potential. And in this episode today, we will talk about why ZCPs are relevant, how they work, where they can be applied, and why they are so beneficial. But we will also cover some technological aspects, terminology as well, and also discuss common misconceptions around, basically applying ZCPs. But if I say we today, it's not just me. Besides myself, we invited again Dr. Johannes Sedlmeier, who is an expert on this topic. Johannes is one of the most frequent guests in this podcast, I would say for good reason, Johannes. And after joint episodes around the topics of digital identity, energy consumption of blockchain applications, consensus algorithm, blockchain's interoperability, and so on and so forth, we will today go very deep into the privacy rabbit hole. Johannes, great to have you here. Thanks for joining our podcast.
Yeah, glad to be here, and thanks for having me again.
Perfect. Yeah, our pleasure. And, I think the listeners, they might know you because every year you have been part of this podcast. But maybe there are a few rare or new ones that don't know you yet. Maybe you can briefly introduce yourself, what you're doing, what your background is. Maybe also talk about how you basically came to the topic of privacy.
Sure. Yes. So my study background was actually in math and theoretical physics. But then for my PhD, I went into the information systems domain, so somewhere between economics and computer science. And I did my PhD in Bayreuth, just as you did. And there I was focusing mostly on blockchain technology. My dissertation was about essentially the limitations of permissioned blockchains, so why they don't solve. They address a lot of the issues of permissionless blockchains, but none of them sufficiently, in my opinion. And then I was also touching a lot of topics that emerged in the context of blockchain, like digital identities, privacy-enhancing technologies. And in my current position as a postdoc at the University of Luxembourg, I'm also continuing those research questions. So mostly about applying emerging technologies like blockchain, digital identities in businesses, and somehow merging technical design questions with also business needs.
Yeah, and that's, I think, in particular, Johannes, why I really, love to discuss with you in this podcast, because it's always that you have the practical, understanding of topics, but also the very, very deep technical knowledge. And this is also like the goal of this episode today, to really talk about these privacy-enhancing technologies, and in particular, zero-knowledge proofs on more, in high level, and to make this tangible, to make this understandable, but also go a little bit deeper into some technical components that it's, not just on the very high level. And I think you're always the perfect guest for that. And what also motivated me a lot to make this episode today is, when we started to work on these topics of ZCPs like a few years back, and you obviously started way earlier than I did. But when we wrote our paper on zero knowledge proofs and CBDCs a few years back, I often felt that people really had, or just a few people had, a good or a solid or a decent understanding of ZCPs. And from my perspective, this now changes, and this is also why we said, okay, we need this episode today, because this is more and more coming. It's embedded in some digital identity applications we talk about later today, and this is why I think this is a very, very relevant episode. But yeah, maybe back to you, Johannes. You said, during your PhD time, where also our paths basically crossed, you came into this topics of challenges of blockchain applications. One definitely is privacy. What fascinated you most on the topic of privacy? Because you also looked into, energy consumption, interoperability, but it seems, at least to me, that you're doing an over proportionate amount on the topic of privacy.
Yeah, actually, I would even say that it's not only privacy, but in general, protection of sensitive information. Because if you look at blockchains, then it becomes quite immediately clear that the replicated processing of transactions is in a strong conflict, not only with protecting sensitive information of citizens and individuals who are using, for instance, DeFi services, but also for companies that want to use blockchain technology in supply chain solutions, for instance, because only a very small part of the information businesses are processing is really meant to be on a transparent layer that is visible either to the broad public for permissionless blockchains, but even in permissioned blockchains where you have, I don't know, a consortium of supply chain companies, they usually don't want to share all of the data, what kind of interactions they have between them, what quantities of material they exchange, and so on. And it was not quite clear how to address this issue because the replicated information processing is one of the core design principles of blockchains. And so that fascinated me quite a bit. And that also brought me into zero knowledge proofs because, in my opinion, this is one of the best cryptographic approaches to address those issues. You cannot address all of the privacy issues with them, but at least a large family of those that appear on blockchains because verifiability is very important. And then it turns out that those improvements in zero knowledge proofs that have happened because there was increased research interest on blockchains can also be applied to other areas. Like, for example, CBDCs, the paper that we wrote, where blockchain was not really a part of the solution, but still you can use it in centralized solutions, essentially, or also in digital identities, where you also have this issue that oftentimes you need verifiability, but still you want to limit the amount of information that you disclose. And so they just appeared quite naturally as a very nice solution to a lot of the privacy issues we see. And because there's also often a lot of emotional discourse around privacy, that's naturally also something that attracted me as a researcher to propose solutions and also hopefully debunk some myths about perceived trade-offs that can be resolved.
Yeah, and I really like the emotional discourse, how you framed it, because of course, as an academic, that's always the myths that you want to, look into if they are indeed the case or not. And I think this was also for me one of the key reasons to look into the topic of ZKPs a few years back, also when we wrote the paper, because it was always said, hey, you cannot have privacy or anonymity on the one hand side and all the regulatory, requirements met on the other side. Like if you think about, hey, you have to be KYC'd, identified as a user, or there have to be sanction screened. There was always said it's not possible to do it both. And I think for a lot of years, a lot of decades, this might also have been true. But with ZKPs, I think you can do now a lot to really work on these very, very deep, topics that go to like civil rights, basically, right? So go back to privacy as a civil right and will impact payments, identity, and so on and so forth. So yeah, that was definitely also something that attracted me and brought me to the topic as well. Yeah, and secondly, what I also liked and where I would agree, it took me actually a few years to understand that. But initially, I started, going into the topic of ZKPs on. I'm a privacy, loving person, so I pay with cash where I can. I try to use VPN where I can. So I'm not saying, I'm doing illegal things. I just think it's my right to do that. But on the other side, this corporate application is, of course, from a business perspective, from a market perspective, way more important to say, look, also companies, they don't want these data to be shared with everybody, or there are very, intense cybersecurity threats if you always share data with clear text, even if not on a blockchain, but in a centralized database, right? And that's, I think, also something where the understanding has grown and grown over the past 2 years. I think we are still early, but that's also something where I see a lot of potential.
I think it's also important to notice that privacy is not only important from a moral perspective or for companies remaining competitive, but there's often also a security implication. Like the more information an attacker can get, the easier they can attack a certain system, like social engineering and so on. And sometimes there are also very immediate economic implications. So for instance, the lack of privacy on Bitcoin, at least no sophisticated privacy on Bitcoin, because once a link between an address and a person, there are ways to basically follow the trace of coins through the network. And so this threatens the fungibility of Bitcoin, which is one of the core value propositions, because usually in a monetary system, you want to have fungibility. But if you know that a certain coin, for instance, was earlier involved in, some criminal activities, then it might happen that there is a small risk that those assets will be seized in the future. and therefore the value might be reduced. And this would really not be a good thing if you want to use it as a means of payment. And that was also, besides the moral reasons, one of the main motivations why privacy coins like Zcash have been introduced.
Yeah. Yeah, and I think this clearly shows why this topic is important, why privacy is important in the digital world, why privacy-enhancing technologies are important in the digital world. And what we want to do today is to look particular at one tool, like basically a cryptographic method that aims to strengthen our privacy, or so-called zero-knowledge proof, ZKPs, as we mentioned before. And yeah, I'm sure that the listeners after the episode will also be similarly excited as we are, at least I hope. But let's start really from the beginning. And with this question, I was inspired by a video I've seen where it said, hey, how would you explain a zero-knowledge proof? Because in the end, it is very complex. There is very heavy math cryptography going on. But maybe starting very, very high level, Johannes, how would you explain how a ZKP, zero-knowledge proof, work, maybe to a kid?
Yeah. So first, we should probably define what a zero-knowledge proof is. And there, actually, the difference of the definition between explaining it to a kid, to an adult, and, I don't know, a software engineer is actually not too big. And so that's essentially a means to convince someone that some statement is true, but without giving away all of the underlying evidence. And so, in fact, basically you want to convince someone without revealing anything more than that what you say is true. And so an example that a kid may understand is, for instance, you want to give evidence that you can open some door with some secret mechanism that you don't want to give away. This could be the shape of the key. This could be a magic word that you don't want to share. There are a lot of things or options to think about that. And so the way you could convince someone is to basically hide this door in a cave. So this is the famous cave example, even though I don't like it a lot because it doesn't tell you how things work on a computer. But in the physical world, basically you would hide this in a cave with 2 exits. And then the person you want to convince is standing in front of those 2 exits. I go inside, and then basically I get a challenge. And the challenge would be enter on exit 1 or enter on an exit 2. And this is random. And so essentially, if I want to exit on the right side every time in repeated challenges, then I need to have some way of going through this door, because otherwise I cannot choose which side I want to exit on.
And I think this repetition, Johannes, is super important, right? Because if I'm in there in this cave and say, hey, look, I know how to get out of this cave, right? And you basically, in the first time you leave at the right-hand side, it could be a 50-50 chance, right?
Exactly.
And in the next side, if it's, hey, now I show you, I leave on the left. And then again, it's still 50%. And the more often you do it, at some point the other person says, okay, you really know the secret. It's not just luck or something that you are leaving the cave.
Yeah, and this interactiveness is also one of the key design features of the first zero-knowledge proofs. So we will see maybe later how we can remove this interactiveness. But first, it was basically this notion of interactive probabilistic proofs, where you have a lot of repetitions, and basically you can decide how many repetitions you want. And by doing so, you can decrease the error probability that you basically accidentally always get the right exit, even though you cannot open the door. And you can get this error rate arbitrarily small, so that in practice it doesn't matter, just as the probability that I at random guess your Bitcoin private key is also negligible for all practical purposes.
Yeah. Okay. So I think this was a good start, with this cave example on how to explain this to a kid. Maybe the Bitcoin private key is too special for the kid, but how would you maybe, go to a little bit deeper, how would you explain it to an adult maybe?
Yeah. So for an adult, one example that I particularly like is proving that I know a solution to a Sudoku puzzle, but without showing what the solution to the Sudoku puzzle is, or in fact, without revealing any of the non-pre-filled numbers. And so in a physical world, you can probably imagine this relatively well, because you can essentially fill out the Sudoku with, for example, cards or small plates with the corresponding numbers. And then basically you put all of the non-pre-filled numbers face down. So you hide them. And then what the verifier would usually want to be convinced of is that in every row, in every column, and in every 3x3 subsquare, every number is only appearing once. And now you can literally do this. You cannot check all of those, well, that should be 9 times 9, so 81 conditions at once. But you can, for example, say, okay, now I want to pick the first row or the fifth column. And then essentially you can have them shuffled. And because if you don't shuffle, you would reveal what the solution is, right? If you just open them one by one. But you can take this row or column away. You can first make sure that they are all facing in the same direction. So basically, if there is a pre-filled number among this row or among this column, you would also put it face down. You would shuffle all of them, and then you would reveal them. And then the verifier can basically check, oh, does every number only appear once? And if this is the case, then this gives us a tiny degree of confidence that indeed this might have been a valid solution. Because if it wasn't a valid solution, then one of the rows or columns or 3x3 subsquares would not have this property.
Yeah.
And so you can repeat this over and over. There are a few optimizations to basically make the degree of confidence you get in every round already a bit bigger. So for instance, you could check all of the rows already, or all of the columns, or all of the 3x3 subsquares. And then again, if you do enough repetitions, then eventually you will probably be convinced that the prover, so the one who is claiming that he or she knows a valid solution, actually has such a valid solution.
And again, the importance here is really the repetitions, because if you do this just once, right, it could be luck. If you do it twice,
Exactly.
It could maybe still be luck. But if you do this 10, 20, 30 times, then yeah, the verifier might be convinced that you indeed solved the Sudoku and, it was not just luck. And secondly, and I think what you mentioned, Johannes, is very important. This was probably too much for the kid, but is now fine for the adult, is that you basically add some randomness to all of that, right? So that you're not always revealing the specific cell and showing you anything, like this is a 1 or something, but you always add this randomness. So even if you do a lot of different checks, you never know the Sudoku itself, right? What in the cubes basically has been in numbers. You just know that this has been fulfilled. So the result in the
Exactly. And that is because you don't reveal the row or column or subsquare directly, but you first shuffle it and then you reveal it.
Yeah.
And by doing so, you have no idea where a certain number was located before the shuffling.
Okay. Let's now go one step deeper and now explain a CKP to an engineer. So what would you say now?
Yeah. So first, maybe, there would be two ways. So first, I would probably be giving a definition, and then I would be giving a construction. So how you do that. But since we're already in the Sudoku, maybe I would start with the construction, because the first thing an engineer would probably ask me is, okay, well, it's nice that you thought about this shuffling, but how would I do the shuffling on a computer? Because you cannot really check that I'm doing the shuffling honestly and that I don't change any of the numbers, right? So in the physical world, I might lock you in a room. I might make sure that there are no cards other than the 81 cards that are already there. And so even if I shuffle behind my back, you can still be convinced that I don't have additional numbers that I can add or interchange. How would you do this on a computer? Because I can't actually look into what your computer is doing if you're doing so. And somehow the argument might look cyclical, because if I convince you that I did the shuffling correctly without showing you the shuffling process, then that sounds a little bit like a CKP again, right? So how do we resolve this conundrum? And the answer would be that essentially we do the shuffling before we open. So what does that mean? We use what is called a permutation. Why do we need this? Well, if it's just about consistency of rows, columns, and subsquares, then actually we just need to make sure that every number occurs once. So there is no additional property that this permutation needs to satisfy. Where it gets interesting is if you want to make sure that also the pre-filled numbers match what you would expect. Because it's very easy to come up with some solution to some Sudoku puzzle, because I can just permute, for example, different rows and use each permutation once. what's interesting is, does this solution actually coincide with the pre-filled numbers in the right spots, right? And so the idea that you can take is, well, what we need is a commitment scheme. So we somehow need to bind the prover to a decision he or she made, such that they cannot change this in the future. This is also where blockchains have been used in the past sometimes with, so you use the hash function, and then you just publish essentially the hash, for example, of the filling of the Sudoku. And what you also have is a permutation that essentially, for example, switches every 1 with a 9, every 8 with a 3, and so on. And now, of course, if you reveal the permutation and, for example, a row at the same time, then by looking at the pre-filled numbers, you would learn something about the solution. Because, for instance, if you see, okay, the pre-filled number should be a 4, the permutation maps a 4 to a 8, then you know what happened, right? So you learn something about the solution. But what I can do is, basically, I can offer you the opportunity to either reveal the permutation and what happened with the pre-filled numbers, such that you can check for consistency with the original puzzle, or you can ask for the new content of a row or column or subsquare, but without revealing the permutation.
But not both, because otherwise you would expose information.
Exactly. So essentially you commit to the permutation, you commit to the whole Sudoku solution, and then you can choose what should be revealed, but you cannot opt to reveal both the permutation and a square or a row or a column. And this, of course, it introduces an additional layer of chance. And so you need to make sure that the error probabilities are computed correctly. But this is how you would implement this on a computer. And for this, you only need a commitment scheme. So a way to be bound to some decision that the prover has made before. And this is actually very similar to a lot of the early zero-knowledge proofs that have been developed in the 1980s and 1990s.
Yeah, let's very happy to take a brief look at the history, like, how this came up, because that's, nothing that just appeared 5 years ago and that's it, right? There was a basically decade-long process around establishing and bringing ZKPs to light, let's say.
Yeah. So the definition is actually from a paper in the mid-1980s that was published by Goldwasser, Micali, and Rakov. And so this paper was called The Knowledge Complexity of Interactive Proof Systems. What's also maybe important, and maybe also a shimmer of hope to researchers that are listening to this podcast, it took that paper around 5 years to get published. So it was rejected.
Can really relate to that.
I believe 7 times or so. Because, obviously the idea was maybe a bit too smart to be acknowledged also by academia at that time. And so what it looked at is so-called interactive proof systems. And what is this? And this also leads us a bit to the definition of a zero-knowledge proofs. So this is essentially an interaction between a prover and a verifier. And the prover wants to convince the verifier of some statement. And people looked into this mostly for theoretical reasons in complexity theory, having the question in mind, well, how many resources do I need to convince the verifier? Can the prover do some additional work to save the verifier work? So for instance, I can convince you of a highly complex statement, but I can convince you by you not doing a lot of computations. So this was the original motivation. But then one question that comes to mind quite immediately is, well, if the proof that convinces you of this statement is somewhat small and easy to check, how much information beyond the correctness of the statement can it really include? And that then led also to the notion of a zero-knowledge proof, in which essentially the verifier learns nothing beyond the correctness of the statement that the prover wants to demonstrate. And so usually the formal definition of a zero-knowledge proof is such an interaction between a prover and a verifier. We have a public statement, which is usually denoted X, and then the prover has some additional information, witness, W, that he or she doesn't want to share. Think of, for example, some private key, the solution of the Sudoku puzzle. for the Sudoku, the public statement would essentially be, well, the Sudoku with the predefined rules and the pre-filled numbers. And then the witness would be essentially all the other numbers that have not been filled yet, which constitute my solution. And then we have two more important properties beyond the zero-knowledge property, which is completeness and soundness. The completeness property usually says, well, if the prover has a valid solution, then he or she should be able to convince the verifier with high probability. So we don't necessarily need 100%, but most of the constructions I'm aware of will give you 100% success rate if the prover has access to a valid witness, to a valid solution. And the other one, and we also mentioned this before already, is what is called soundness. So the soundness guarantee says, essentially, if the verifier is convinced, then with very high probability, the prover actually has a valid witness. So you can think of this a little bit as the rate of false positives. So how likely is it that the prover does not have access to a valid witness, does not know a valid Sudoku solution, but still can convince the verifier? And usually you don't require like 99.99% in this definition, but you're happy with something like a third or 1/2, because then through repetition you can get this soundness error arbitrarily small.
So this really shows again why this repetition is important, and basically the three key ingredients basically being completeness, soundness, and zero knowledge, obviously.
Exactly. Yeah. And then what's important from my perspective, it's not a very formal distinction, but it's very helpful for the mental model, I think, is the distinction between special purpose and general purpose zero knowledge proofs. And so you can think of the special purpose zero knowledge proofs as some sort of a mathematical trick that the prover performs, usually in their head, and then shows the verifier some interesting things. Like, for example, in the Sudoku puzzle, well, you can choose between the columns, the rows, and the subcells. Or, for example, if you're familiar with digital signatures, they are usually connected to a construction which is called knowledge of a discrete logarithm. So you perform a cool mathematical trick that convinces the other side that you indeed know some secret, even though you don't share this secret, right? So this is quite commonly used in digital signatures. And with those, you can really only prove very specific statements. And you don't have a lot of flexibility. So basically, every time you have a new form of a zero knowledge proof, I want to prove a new statement, somebody needs to come up with a clever trick that convinces the other side of exactly this statement, but it's not very flexible. And this basically describes the first 25 to 30 years of zero knowledge technology. But then in the mid-2010s, so 2014, for example, when we saw Zerocash and then Zcash, slightly before that, also what is called the general purpose zero knowledge proofs became practical. And with those kinds of zero knowledge proofs, you can essentially prove any kind of statement with a generic mechanism that essentially proves the correct execution of any kind of algorithm. So why does that make sense? Well, in the case of the Sudoku puzzle, for instance, we had this nice mathematical trick in mind where you can pick between rows, columns, and so on. But another way, if I knew to convince you of the correct execution of an algorithm, what I could literally do is I could write some code that checks some probable solution to a Sudoku puzzle if it is actually a solution. So you really go through all the rows, through all the columns, through all the subsquares, and so on. And then if I can prove to you that I know some input such that this Sudoku verification algorithm returned true, then this would also be a zero knowledge proof of the correct Sudoku solution. And so by doing so, we have a generic mechanism that can prove essentially any statement that you can formally describe with an algorithm.
And I mean,
this is then very powerful.
Yeah, exactly. That's what I was about to say. I mean, for adoption, that's of course key, right? If you don't have like one code, one application you write for a very specific use case, example of Sudoku, right? I mean, it's nice if you have that, but how often in practical life, you need to solve or to prove specific things from a Sudoku. But if you think about about identity, about privacy and payment topics, where it's often very, very complex, that's of course a complete difference if they are in this sense like general purpose. And would you also say, Johannes, that this transition from having these general purpose CKPs, also having efficient solutions that are maybe quicker to compute, to prove, to verify, that this was kind of somehow kind of the key reasons that CKPs have reached like the stage of their development where they are today, so that they progressed?
I would say so, yeah. So we knew since the mid-1980s that those zero-knowledge proofs exist for any kind of statement, and in particular for the execution of any kind of algorithm. But at that time, there were no efficient constructions that were working on an average computer. And so this started to change in 2012 when what is called ZK snarks were introduced for the first time. And they were then also used at large scale in Zcash, basically in the first prominent application. And since then, they have taken off because their use in blockchain privacy was just very useful. Turns out actually that most of the funding was not really stemming from privacy projects, but rather from scaling projects, which have a very close connection to zero-knowledge proofs. And oftentimes the terminology is a bit misleading there. So there it's really about the shortness of the proof size. So the so-called succinctness property, we already said earlier that basically if the proof is not too large, then it also cannot include a lot of information beyond the correctness of the statement. And it so happened that the zero-knowledge proofs that were used in Zcash had this property that they are pretty small, and their size was independent of the size of the statement you want to prove. And so the idea that you can use this for batching transactions and for compressing information on a blockchain ultimately led to the development of a lot of scaling applications. And they eventually really provided a lot of funding for technology that is very closely related and can usually be transformed into also zero-knowledge proofs. And in my opinion, this was like the key reason why in the last 10 years, the performance and the maturity of zero-knowledge proofs in their general purpose flavor just increased drastically and in an unprecedented way that I think hardly any of the expert cryptographers expected. So that was really amazingly quick because there was so much funding and then also research interest in improving this technology.
And that's really an important aspect that, that the listeners shouldn't misunderstand that we talk about CKPs primarily from this privacy angle. This is just, the focus we picked for this episode, but there is also the scalability angle. I mean, if you think about CK roll-ups, where, as you said, you batch transactions, and have different transactions than in some kind of L2 or off-chain environment. That's, again, also a very, very important application of CKPs also today. A lot of money is going into developments here, but for today, we are not focusing on them. But I just wanted to mention this again, maybe something, we can also discuss in a future episode. But let's now go a little bit deeper and we zoom out a little bit from the more technical part now, and good to see that listeners are still with us to go a little bit higher level again to say, okay, we understood how CKPs basically developed a concept like 40, 50 years old. It was more specific, not generally applicable, general purpose. It was not efficient yet, and it basically started with Zcash then, I think 2012, you said, right?
Or Zcash was 2014, so Zero Cash, Zcash, yeah. 2012 was essentially the ZK snarks that then were used in Zcash and also a lot of other blockchain applications that used zero-knowledge proofs in the next years.
Okay,
so
got
the first
it. So
efficient construction,
first
of those
efficient
general purpose
construction first. Like larger applications. I mean, with Zcash, there was, basically, millions, probably billions, and funding. So really making this practical, basically. But again, this is almost, or is 10 years back now. What would you say? Which use cases can CKPs use today? Or so what can we use CKPs for, primarily again in the context of privacy, or what are use cases that have emerged maybe outside these, let's say, niche crypto specific use cases, which again I think have a right to stay and a place, right? But it's not the ones that will concern most of the corporates out there in the world.
Yeah. So to understand this, so I usually structure this into basically applications that are practical and in use already today, and those that are at the brink of being practical, and those that are still cool from an academic perspective, but still largely unpractical. And so the main reason for this distinction is one of the key also challenges of using zero-knowledge proofs. And this is that the general purpose zero-knowledge proofs usually have a very high prover overhead. So that means that the prover needs to work very, very hard. Think of like 1,000,000 times harder than just showing that the statement is correct by naive verification. Yeah, so basically, if I run the Sudoku verification algorithm, this takes me on my computer, I don't know, maybe a few milliseconds. But if I want to prove that I run the Sudoku verification algorithm correctly, this will probably take me seconds, probably even a few minutes.
Okay, yeah, and for a lot of applications, of course, that's a showstopper, right? Because you don't have seconds or minutes.
Exactly, or because the native execution already lasts seconds, and then an overhead of 1,000,000 will really make this impossible. Yeah. So since we're already talking about this, so this one of those examples where already the native execution is a lot of effort and you don't want to bear 1,000,000 times overhead would be zero-knowledge machine learning. So what you can think of is, well, I want to prove to you that I know a certain prompt such that Llama 2 or GPT-4 returns a certain response. So people want to bring machine learning also to blockchains, and so they want to prove, for instance, that a certain machine learning model was executed correctly, so that the inference happened correctly. Maybe you remember in the past there were some discussions where people were suspicious that instead of, I think it was GPT 3.5, they were suspecting that it was still GPT-3 that was being used, even though 3.5 was being promised for the money you were paying. And so there was the accusation of OpenAI saving some resources, if I remember this correctly. And so zero-knowledge proofs would give you an opportunity to essentially prove, yeah, it was indeed this model. And for example, I only reveal a certain part of the prompt because I want to keep the prompt private. Think of an artist, for instance, who is doing some arts with LLMs. And there you can imagine that this is pretty cool and people are working on improving this. But as of today, it still takes like minutes to hours on a computing cluster to prove the correct inference of a single token, so a fraction of a word. So this is not really practical right now, and it would need very big improvements to make this practical, because of course this 1,000,000 times overhead also costs you a lot of money. And it's nice, there are some improvements that can be done. So for instance, in machine learning, there are a lot of matrix multiplications. You can make proving correct matrix multiplications pretty efficient also with general purpose zero-knowledge proofs by doing some additional tricks. So there is hope, but it's still largely impractical. Now, what is practical? So first of all, privacy coins like
Zcash, Tornado Cash. Yeah.
Exactly. Those are then the mixers, or dark pools. There are different names for this. So essentially unlinkable payments or unlinkable deposits and withdrawals, even though the underlying storage is publicly visible. And those are all of those privacy coins.
And publicly usually visible, you basically mean permissionless blockchains, right?
Exactly. Yeah. Yep. And so there you usually just prove, well, a certain transaction is legitimate. When is a certain transaction legitimate? Well, you should make sure that the sender has signed it, so has authorized it, and that the sender's balance is sufficient for sending the money, so you don't get into a negative balance, and that the total sum of assets involved in this transaction don't change, because this is what matters for the rest of the network, right? For me, it's not really important what you and, for example, your co-hosts are doing in your interactions. What matters to me is that the total supply of the of the monetary system doesn't increase, because that would reduce the value that I have. And so you need to somehow prove that the amount by which your balance increases is exactly the same as the amount by which your transaction partner's balance decreases. So those are the kinds of statements that need to be proven.
Before we jump back to today's episode, let us introduce the Digital Euro Conference 2025 to you, a must-attend event on the future of digital money. Taking place on March 27th in Frankfurt and online, DEC 25 brings together leading voices and organizations shaping the financial landscape. Confirmed participants include representatives from various central banks, such as Deutsche Bundesbank and the central banks of Brazil, South Korea, Netherlands, and others, as well as stablecoin issuers, banks, companies from the industry, startups, etc. With a cutting-edge agenda covering retail and wholesale, CBDCs, stablecoins, and tokenized money in general, this is your opportunity to connect with industry leaders driving the future of finance. You want to participate? As an official event partner, BFRR gives away one free ticket for physical participation in Frankfurt. If you are interested, please write us an email to info@bfrr.de by January 31st. And learn more about the conference on digital-euro-conference.de. Now, back to today's episode. Yeah, and that's very interesting, because that goes again, and we will put the document in the show notes, what we also proposed in our POC, our solution back in the days on CBDC. And what for me was so relevant here is basically, we are asking, or ZCPs kind of, or in this context, there are questions asked that are the same as for traditional payments today. It's like, if you do a bank payment, it's like, is this really the person's authorization? Does this person has enough money? Maybe does the recipient exist, right? So is the IBAN given, things like that. And that's kind of one-to-one the same, but just that you are not sharing this in clear data, right? But just saying, convincingly sharing with a proof, which of course is a complete different dimension in terms of privacy. But for me, it was very important in my head to understand the link, while being so different, that exactly the same results are somehow trying to be extracted, even if it's here just a proof and not a clear data for information.
And the paradigm shift you essentially need to make is, instead of revealing all of the data and then leaving it open for the future, which of this data is being accessed by, for instance, a bank or a regulator, you basically need to decide beforehand what kind of information do you disclose and what kind of statements do you want to prove. And then you can be completely sure that in the future you cannot extract any additional information. So you need to make sure that you are asking the right questions in terms of compliance ex ante, and then you prove exactly the compliance with those kinds of expectations, but nothing more. So
that's super interesting.
Proofs give you a guarantee of data minimization, and this also demonstrates that it should not be mixed with anonymity. So of course you can use zero knowledge proofs to get anonymity, but usually we don't necessarily want total anonymity. Maybe we want to reveal some of our identity attributes, maybe our nationality. Maybe we also need to prove that we are not on a certain sanctions list, but we're just answering the questions that were being asked, and we don't reveal anything beyond this.
Besides these private payments or privacy coins mixers, which further use cases would you say are practical already today?
Yeah, so in DeFi, we do see quite a few applications. So for example, for sealed bid auctions. So if you want to have an auction, then what's often desirable is that the bids are not public, but the naive way to implement an auction on a blockchain with a smart contract would reveal the amount everybody is bidding. And so with zero knowledge proofs, you can essentially do a two-step process in which you first send a commitment to your bid, and then later on you essentially reveal this. Now the question is, where do you need the zero knowledge proof? Well, for instance, because you should prove that you do indeed have the money for the bid and that you have sufficient funds. This is also closely related to another application, which is, for example, anonymous voting. So you want to make sure you vote for a certain improvement proposal, for instance, but maybe you don't want to reveal who you are, but you still need to prove, for instance, that you own a certain share of the governance tokens, such that the weight of your vote is reflected in the right way. Another important part is, for example, if a DAO wants to bid for something. So there was this, I think it was called Constitution DAO, that wanted to bid for a certain interesting artifact in connection with the US Constitution. And they essentially gathered funding, and then the DAO participated in the auction for this artifact. But then they were just slightly overbid because the DAO's funds were public. And so everybody knew how much they can bid, right? And so if you want to conceal this and to allow, for instance, a DAO to also manage funds without revealing to the public how much the DAO has, such that you can know how much they will bid, this is also a nice opportunity. And again, you still need to prove the compliance with certain rules. For instance, that the DAO cannot spend more than what they totally have, and so on. A similar approach is also in combating what is called maximal extractable value. So there is a lot of issues with front running and back running and sandwiching and all of those things in decentralized finance, because the blockchain and the mempool are both public. So everybody can see not only the transactions that have happened, but also the transactions that are waiting for being approved, and then abuse this information. And so what you can again do there is, for instance, you have a commit reveal process in which you first only send the hash of the transaction, and only once it is included and sorted and ordered, you basically in a second step reveal what it was. So for instance, your lottery bet or your bet in an auction. But still in the first place, you probably need to prove that you have, for example, deposited a certain collateral, such that if you refuse to open it in the second step, which might be in your interest because, for example, some exchange rates could have changed in the past that make this transaction unprofitable for you, you could just say, well, then let's just not open it to avoid that. But then there needs to be some form of collateral. And so you need to prove that whatever is in this transaction is collateralized sufficiently. So those kinds of games.
But this is then primarily, Johannes, I would say, very, let's say, DeFi native Web3 type of applications, right? So I guess there are also applications that are more, let's say, addressed towards or targeted towards mainstream.
I think they are still the most broadly used form of zero-knowledge proofs, but I hope that zero-knowledge proofs will also appear more prominently quite soon beyond blockchains. And so some of those applications are, for instance, what is called zk-TLS. So this is also pretty cool. So you can essentially prove statements about encrypted web traffic. What can you do with this? So one thing I can do with this is, for instance, prove to you that some information is coming from a certain website. Now, it's actually, if you take it seriously, not purely ZKP. You need a little bit more even. You need to involve a third party. But then you can prove to this third party, for instance, that your PayPal balance has a certain amount, or that other information that you see when you go to your PayPal account is true. For instance, I don't know, when was the account opening, to have some reasonable form of proof of humanity.
So it's basically exposing or proving some information from a different website, basically?
Yeah, so essentially you're proving that you're revealing information from an encrypted communication with a website, which is assured through the digital certificate that, for example, PayPal has, right? PayPal has this certificate from a certificate authority, and so there is a root of trust. And so because you know that the information like the balance is coming from paypal.com, somebody else might trust it.
Okay, got it.
And so this is pretty cool. This has also been used, for instance, for easy crypto on-ramps. Like you used an email that is also somehow connected to encrypted web traffic, and you can prove that there was a certain confirmation of a deposit, and therefore it is legitimate that your crypto holdings are increased, for instance. There are also what is called ZK middle boxes that are currently being looked at. So for instance, today, if you are in a VPN, oftentimes there are certain parts of your communication are decrypted and exposed to the VPN provider. So for instance, the DNS lookup. And so if you want to prove, for instance, if you're in a school network, that you're not visiting an adult page among one of the, 100 blocked addresses, but still you don't want to reveal anything more for security or privacy reasons, then you could use this and again prove a statement about your encrypted traffic, which is, well, I'm not visiting one of those 100 forbidden pages, but you don't need to decrypt it and therefore expose it to, for example, an attacker who has hijacked the server of the VPN provider. This is practical today from a performance perspective, but still not really widely used. There are a few small startups that are trying to sell this, and in particular for this CKTLS, so authentic data from third-party sources who can't even do anything about it. So PayPal couldn't address this issue, even though they don't maybe want you to sell authentic PayPal data, they cannot keep you from doing so. It just makes it more convenient than handing over your password to somebody else, because this is obviously not great from a security perspective.
And I'm now, Johannes, playing devil's advocate again. So I think it's all, as you mentioned, it's all really cool use cases, and my mind is already thinking about in which contexts, for which companies this could be relevant. And it's very good to see that it's practical, but I think it's still a few years away from, let's say, commercial viability in some perspective, because this also takes years, sometimes even decades. I think are there, and I'm particular because I'm coming from this identification KYC KYB topic. Isn't this also a use case that is a little bit earlier basically to reach and maybe also potentially way higher? What do you think about this use case of CKPs around identification?
Yeah, so for me this is also the most promising candidate for large scale adoption in the next maybe 5 years. So we've already discussed this also in our episode about the European Digital Identity Wallet and the corresponding privacy challenges. So indeed, there is currently a big discussion about the privacy provided by the European Digital Identity Wallets, and also the necessity for certain use cases, like, for example, proving that you're older than 18 on certain, again, adult pages, for instance, where you really don't want to disclose linkable information. And so the topic of what is called anonymous credentials, so essentially identification and authentication without leaking anything more than what was being asked for, is probably also the oldest application of zero-knowledge proofs in general. So already in the early 2000s, there were papers about special purpose zero-knowledge proofs that you can use for login and authentication, like I prove to you that I'm a German citizen who is older than 18, or I prove to you that that my first name is Johannes and that I'm registered in Bayreuth. Those kinds of statements. The issue you have with the typical way of doing digital certificates, or as we call it now, electronic attestations of attributes, is that they are digitally signed and they include a lot of cryptographic metadata. Like, for example, the value of the signature, what is called the binding key, so the public key of the holder. There is a revocation ID, and there are other unique cryptographic identifiers. And therefore, in a common, what is called verifiable presentation, in which I show you those attributes, I would disclose way more information than the relying party was asking for, in particular those unique cryptographic identifiers. And what zero-knowledge proofs offer you is a means to basically remove all of those unique cryptographic identifiers, of course, except for the fact if they are explicitly asked for. But this is usually not the case. And so there are quite a few challenges why the early and still or already quite mature zero-knowledge proofs developed in the early 2000s are not really practical for the European Digital Identity Wallet today. For instance, because they are not supported by the hardware that is out there. They are not supported by the credential formats, like, for example, mobile digital driving licenses or X509 certificates. But because we now have quite powerful general purpose zero-knowledge proofs, we can essentially stick to the existing infrastructure and then put the general purpose zero-knowledge proofs on top of this. And there was a quite recent publication by Google researchers who have made basically the general purpose zero-knowledge proofs very performant even though they are applied to this legacy infrastructure where performance of zero-knowledge proofs was not some design criterion people had in mind at that time.
And I mean, it's kind of clear that these methods, even if they are a few decades old now, there are still challenges. And you talked about hardware restrictions and others. And here we definitely put also the episode you mentioned into the show notes on ZCPs, also for the European Digital Identity Wallet, so that everybody can listen this episode if he or she likes. But I think from this identification perspective, and I'm glad we are aligned on the potential here. Let's say. And this is like a personal experience. What I really struggle with is generally with the unnecessary steps of user identification. So what do I mean? I had this before here in Germany. I'm customer of a specific bank, and I opened a private customer, and I opened a business account. I had to do complete KYC again. So video ident, showing password. I think everybody knows this in Germany, which for me personally just sucked. I had to get a power of attorney for a third account, and I had to do it again. So in the end, which means this is data the bank already had on me, so it's unnecessary for the bank. It costs money, like 10 euros per KYC, besides all the data security stuff that is going in the back. It just sucks for the end user because I have to do the step 2 times unnecessarily, right? And this is why I'm personally, and also with the startup Hakata, we are building very enthusiastic about this, because imagine a world where you can really reuse this identity. And I know that European digital identity is also going into this direction, but in a way that it's also securing my privacy and not sharing all my ID documents, when I buy a beer, that this is where I got it, this is where I live, this is, how old I am, but just to prove I'm older than 18, yes, I'm a European citizen, blah, blah, blah. That this is, I think, has really, really great potential. And secondly, to conclude, that is really also what we also started to talk about before, the topic of age verification, basically, right? Which is a topic very, very, very important in European regulation and politics as well. So how can we basically make sure that, children, for example, are protected when it comes to social media, when it comes to, war scenes, when it comes to adult-only stuff, content, right? And I think here, this is, again, another practical use cases where ZCPs can play a very, very good role. And luckily, the EU seems to see that, despite the challenges we are having. But this is why I'm personally very enthusiastic about this identification use case for ZCP.
Yeah, so I really hope that this will be the first, really large-scale adoption of zero-knowledge proofs. I would say now, with this recent publication by Google, it's not really a technical issue anymore. So far, it was a technical issue because there was nobody who has implemented this to run on a mobile phone within a few seconds. Now we have this, and so now also the arguments that can be expressed by critics who maybe don't want to take the burden of implementing the zero-knowledge proofs, or who don't value privacy as much, are getting weaker, because now we have a technology that can help us implement data minimization that is also mandated by, for example, the GDPR in an essentially perfect way. So we now know no more information than was actually asked for is being revealed. And now the only thing that's separating this from large-scale adoption is essentially recognition by standardization bodies, and also support by, for example, the German BSI and other security agencies that look into the security of certain technologies. And since this is a 40 years old research endeavor, we know, at least in academia, that those kinds of methods are established and bulletproof. And so there is really only few reasons remaining why this should not be standardized and recognized broadly.
And I think if you look kind of at history, right, where we stand or how this was for different innovations, there is always, you have good idea, it progresses, you have solid use cases, then you also find a product market fit in terms of, business commercial viability. And then you have all these other initiatives that are super important to foster adoption, which you mentioned before, like standardization, right? That specific institutions allow this auditing, right? Is also, how can you make sure, because this is the thing, this is privacy stuff, right? You need to trust you need to trust something, right?
Mhm.
In this, I mean, you don't trust a specific person because you don't have like a middleman here, but there is still somehow some level of trust evolved, even if
Somebody
you want
implemented the
exactly.
software for proving.
Exactly. Yeah. It's just a different level of trust. And for this, you need auditing, things like that. And my hope is really that, we are now entering this next phase. And again, it felt for me, to be honest, like 5 years back, right, Wild West, like, and great idea, great concepts, but now it seems to come, and it needs to be supported by all these other initiatives. Otherwise, it will not fly. I mean, that's just how it is. But again, I have hope, due to the benefits it does, that this technology will fly, will be recognized, and that's just a matter of time until we see this. Let's say kind of in the back end for any type of application where it makes sense, of course. Not for the sake of implementing it, but for the sake of a problem that is solved, basically. Cool. Maybe we are already talking 1 hour, so time really flies. Maybe we try to come to some last questions when we come to Outlook. So we talked about, Johannes, that ZCPs have made tremendous progress. There are still challenges. We talked about standardization, auditing. I'm sure there are more if we think about it and discuss that. But what do you think it further needs for ZCPs to become a mainstream technology? And this I really mean, that it's just used heavily in a lot of different applications in the back end. I don't know, maybe like the internet today, maybe that's too much, right? But what do you think is needed to reach this stage?
Yeah, I think on the one hand, of course, we all know that privacy always has a quite difficult position when it conflicts also with economic goals, like, for example, collecting more information. So oftentimes the motives to implement privacy are then of regulatory nature. So of course we need more appreciation of privacy. In DeFi and blockchain, we have this naturally, because there it is pretty obvious that information disclosure is excessive if it is replicated. But in the centralized system, this is maybe not as much a concern as of today, because we are used to giving away a lot of information to entities that we usually even trust, like providers of certain services. So we need more appreciation. And then, of course, on the other side, we also need to reduce the barrier to implementing such solutions. And I think it's important to notice that there is not only a performance challenge, so it's more costly to generate those proofs, and potentially also involves more latency and therefore also impacts user experience. So of course, we need further improvements on this. But on the other hand, also implementing zero-knowledge proofs is still pretty complex. So the common way of implementing this is through new programming languages, so-called domain-specific languages, that are usually relatively low level, because in some sense they need to reflect the arithmetic operations like multiplications and additions underlying a certain program. So essentially, zero-knowledge proofs are mathematical cryptographic objects. They only understand multiplications and additions, and so you need to write your program, your algorithm for which you want to prove the correct execution, in a way that translates easily into multiplications and additions. And so those languages are usually relatively cumbersome, and there's only a handful of experts who have really mastered them and can also implement this without any security issues. And so you need to have a solid understanding of cryptography, finite fields, and so on in your mind, usually, if you implement this. And of course, this also requires quite a lot of tedious implementation or re-implementations of algorithms that we already have, just to make sure they are verifiable. And so one of the big developments that has started around 3 years ago is implementing what is called zero-knowledge virtual machines. What they can do is essentially they can work with any compiled bytecode that comes from a higher level programming language. So for example, C, Java, Rust. You compile this down to LLVM bytecode. This is something that already happens today. And then you can feed this bytecode into a virtual machine, and this virtual machine will then prove you the correct execution of exactly this bytecode. And so you don't, as a developer, you don't have to care anymore about the zero knowledge proof specific parts. You only consider this as a black box, and you use your existing code bases. You compile them, and then you feed them into this virtual machine. And what you get back is evidence that this algorithm was computed correctly. And this is very nice, because then you don't need to understand anything about zero knowledge proofs anymore. You can work with the existing code bases that have already been audited. The trade-off is that those virtual machines are, of course, less efficient than the handcrafted domain-specific language-written code. And so the performance penalty there is even higher. And so right now, that's why there is a mix. Basically, the zero-knowledge virtual machines are still in development. They're also using tooling that is developed in the handcrafted side of the economy. And over time, I expect that as the performance of those virtual machines matures, there are more and more incentives for software developers to directly go into those zero-knowledge virtual machines, because then there's less vulnerability for errors by handcrafting those what is called circuits. And this would also open us the opportunity to use a much broader space of applications, because then, I don't know, if I have an idea, a nice idea that I want to prove the correct execution of some of the programs that are running on my computer today, because maybe I can make a cool smart contract that makes value out of a certificate that this was executed correctly. I don't need to implement millions of lines of codes again. I can just use this tooling, put it into the zero-knowledge virtual machine, and get confirmation that this was executed correctly.
Very easy, right? For this adoption, that would be, I think, like a game changer to have this in a scalable, efficient, trusted, somehow whatever trust mean, but audited setup. But again, also here we need some standards to emerge. We need a kind of auditing guidelines to emerge. Of course, we also need, and I think that's key, really smart brains to do all this work, right? So it needs good engineering skills as well. And what I really liked in the beginning, what you said, is more appreciation of privacy, and that's something I, for my presentations, I often like to finish with this one slide which says privacy is normal, which is one of the key messages of my presentations, because so often and this goes back to how we motivated, we kind of both came to this topic somehow in a different but similar sense as well, that we do see a lot of efforts that privacy threshold seems to be lower, more surveillance actions for specific things, in the sense, and they are all argued for reasons which we have to do this for regulation, right? We want to make this more secure. And I'm not saying we shouldn't have any of them, right? But we should be careful that there is always a trade-off, and there is not a strong lobby, I would say, for privacy, because the lobby on the other side is way, way bigger. So I think it needs, for us, for the people that like privacy, somehow also to step up. I mean, I don't want to get philosophical here, right? But that's, I think, an effort that we all have to work on. We also want to contribute towards with this podcast, because we don't want to get this privacy lost, because otherwise we have way more severe problems in a few decades or 100 years. I don't know. And I think this is a great technology with great potential if we play it right, in a sense, right? But
we somehow need to address this seeming dichotomy between privacy and compliance, and that's also why zero knowledge proofs are sometimes termed programmable privacy. So essentially, there is not either anonymity or complete transparency. Zero knowledge proofs allow us to pick any position within the spectrum and to prove compliance with certain rules, but giving us also assurances that no more information is leaked than what we're actually asking for.
Yeah, and this joint perspective needs to be established. I mean, I'm also discussing a lot with regulators, different roundtables on ZCPs, because also for them, obviously, the topic is very new. And in the beginning, I'm not sure how it was for you, Johannes, but when I first heard of the topic of ZKP, it was similar than Bitcoin. I didn't really get it, and I was like, hey, it's too good to be true. This cannot work. But then I went into the rabbit hole. Not in the code, of course. You're way deeper into that than I am, but we need this education as well, and this is also what we want to contribute towards with this podcast, to get all different stakeholders on these tables to discuss such things, because that's kind of where the future is heading, and all of these stakeholders need to be involved somehow. Cool, Johannes. Is there anything more you would like to share at the end of this podcast? So I think we covered, a lot on CKPs, from where it started, how it started, what it is, what are benefits, what are disadvantages or challenges, what are use cases, what does it need to, make CKPs a mainstream technology? Is there anything more you would like to share? Or are we good with this 1 hour and 10 minutes?
I think we're good. I just want to reiterate again that basically there is also this succinctness side of zero-knowledge proofs, which often causes terminological confusion. So essentially, just like the zero-knowledge property is a property of a proof system, so a process in which a prover convinces a verifier, succinctness is a different property, and this is this notion of being short. And this is actually what is used in those scaling projects. So many of the ZK VMs and zero-knowledge rollups that you see in the wild are actually not zero-knowledge. They are just succinct. So this is very important to keep in mind. And one could do another episode about applications of succinct proofs and what people now tend to call verifiable virtual machines, where essentially the focus is not on privacy, but on efficiency of verification and therefore scalability. The second thing that's maybe also important to keep in mind is that also zero-knowledge proofs have limitations. So the prover has to have access to all of the information he or she wants to prove. So what we cannot cover is things like, for example, shared state, in which multiple parties, for example, hold a certain fraction of a liquidity pool, but don't want to share their private information with others. There you need even more powerful cryptography, which is then usually multi-party computation, which can be thought as a generalization of zero-knowledge proofs, but that also happens to be even less performant and less mature. Zero-knowledge proofs are not the end of what's possible with cryptography, but it's now a pretty mature technology that already helps us solve a lot of very hard and practically relevant problems.
Yeah, thanks for making these clarifications, Johannes. And I think definitely something to consider, to have another episode more focusing on the succinctness and the scalability applications, CK rollups, etc., because they are heavily applied. There is a lot of VC money going into that. So definitely something to consider. And also, please, for the audience, dear listeners, if you think an episode for that would be interesting for you, please let us know. Then we will definitely incorporate this into our decision. Well, then thanks, Johannes, so much for being with us here today. It was really a great pleasure. I'm sure we will have another podcast episode, definitely way more than one, because there is always exciting things to talk with you. And of course, also, dear listeners, great that you all participated and reached the end, even if it was definitely technical at some parts. But I think you cannot talk about CKPs without any technical stuff that doesn't make any sense. So I hope this was the right level for you. If you like this podcast, please recommend us, refer us to your friends, your colleagues, whoever is in this digital money space here as well. Give us a review on the podcast player that you are using. Become part of our community. We have a Telegram group. You find the link in the show notes. And support us on this journey jointly to educate or increase education, improve education when it comes to digital money, digital assets, and basically the future of finance. In this sense, thanks so much, everybody. Thanks again, Johannes. And see you next time.
Bye-bye.
The views expressed are solely the personal opinions of the hosts and are provided for informational purposes only. This podcast does not offer financial or investment advice. Always conduct your own research and make well-informed decisions before investing. Please be aware that the hosts and guests may hold cryptocurrencies or digital assets discussed in this episode.